Hi everybody, Mrs. Pesic here. We are going over the solutions to the Chapter 7 practice test. For number 1, it says 6 different books will be displayed in the library window. How many different arrangements are there? So for arrangements, that means you're going to have a permutation. So 6 different books will be displayed in the library window. How many different arrangements are there? That would be 6 permutation 6. So 6p6. That means 6 factorial over 6 minus 6 factorial. That's 6 factorial over 0 factorial. 0 factorial is defined as 1, so we get 6 factorial over 1, which is 6 times 5 times 4 times 3 times 2 times 1, which is 720. You could also have found this out by saying, here's the 6 places that I'm going to put these books. How many places do I have, or how many books do I have for the first spot? 6. Once I've chosen that one, how many choices do I have left for the next spot? Well, now I'm down to 5 because I've already used one book. Now what about the third spot? Now I'm only down to 4, and so on. How about number 2? The code for a lock consists of 5 digits. The last number cannot be 0 or 1. How many different codes are possible? Order does matter because we want a lock that is 2, 3, 4, 1, 9 to be different than 2, 4, 3, 1, 9, right? We want these to be different, so the order does matter. So that's why I wrote yes, but I don't think I would even bother solving it with permutation. I would just do the what we were just talking about, which is make the 5 blanks for the 5 different digits, and there's 10 digits possible. So from 0 to 9, that's 10 digits for the first, 10 possible digits for the first spot, 10 possible for the next spot, and so on until we get to the last spot. Here we're not allowed to use 0 or 1, so that just means we have 2 through 9, 2, 3, 4, up to 9, and that's 8 different numbers there. And when we multiply those all together, we do get, I believe, 80,000 possibilities. For number 3, the 3 best essays in a contest will receive gold, silver, and bronze stars. There are 10 essays, and how many ways can the prizes be awarded? Does order matter? Yes, because, you know, Susie might get the gold and Johnny the silver, but then Johnny might get the gold and Susie might get the silver, so order does matter. So we're going to do 10p3, which is 10 factorial over 10 minus 3 factorial. Since order matters, we do not need the extra, times 3 factorial in the denominator. So 10 factorial over 7 factorial turns out to be 720. You could also say to yourself, I've got to award a gold, a silver, and a bronze. Gold, silver, bronze. How many people is it possible to win the gold? Well, there's 10 people in this contest, 10 different essays. So that's 10. But once I've awarded that gold, how many people left to have the silver? Well, now there's only 9 left. And then what about the bronze? Now we're down to 8. So that gives you 10 times 9 times 8 is 720. How about number 4? In a talent show, the top 3 performers out of 15 will advance to the next round. In how many ways can this be done? Does order matter? No. And the answer, why does order not matter here? Because we're just taking the top 3 performers. We're not ranking them. We're not saying, oh, you were first, second, third, and so on. So it's just 15c3, which is 15 factorial over 15 minus 3 factorial times 3 factorial. Remember, if this is a no here, then we will need that extra term here. All right, and so we get 15 factorial over 12 factorial times 3 factorial. That ends up being 15 times 14 times 13 over 6, which is 455. For number 5, in a box of 25 switches, 3 are defective. What is the probability of randomly selecting a switch that is not defective? Does order matter? No, you're just grabbing a switch out of the box. But to figure this out, you're going to find the probability of randomly selecting a switch that is not defective. We're going to use the complement. So we're going to say that's going to be equal to 1 minus the probability that the switch is defective. Well, there's 3 out of 25 switches that are defective. So the probability of pulling a defective switch is 3 over 25. So the probability of not pulling a defective switch is going to be 1 minus 3 over 25. And that gets us to 22 over 25, which is 0.88. For number 6, there are 12 E's among the 100 tiles in Scrabble. What is the probability of selecting all 4 E's when selecting 4 tiles? Does order matter? No. But I wouldn't even go bother solving it that way. I would just, again, assume, what about my first draw? What about my second tile? What about my third tile? What about my fourth tile? What's the probability of drawing an E? Out of the 100 tiles, there's 12 E's, so it's going to be 12 over 100. Assuming that that first one was an E, now what's the probability that our next tile is going to be an E? Well, now we're down to 11 E's out of only 99 tiles left. And then what about the third draw? Well, that's going to be 10 E's left out of 98, and the fourth draw, 9 E's left out of 97. And I will let you multiply this out because I didn't do that. So I'll let you multiply those numerators together, multiply those denominators together. All right, for number 7, it says the table shows the results of rolling a die with unequal faces. Find the experimental probability of rolling a 1 or a 6. The probability of rolling a 1 or a 6 would be equal to the probability of drawing a 1 plus the probability of drawing a 6. So the probability of drawing a 1 is 26 out of these 100 numbers. I added them up, it's 100. And then probability of rolling a 6 is going to be 29 out of 100. So we add those two together, and the probability of rolling a 1 or a 6 is going to be 55 over 100. Now, the question you might ask is, well, you know, if we're doing an or situation, rolling a 1 or a 6, shouldn't we be subtracting something? Well, sure, we could. We could say the probability of rolling a 1 or a 6 is the probability of rolling a 1 plus the probability of rolling a 6 minus the probability of rolling a 1 and a 6. Well, can we roll a 1 and a 6 on one roll of the dice? No, only one number is possible, not two different numbers. So that's why really we would get 26 over 100 plus 29 over 100 minus 0 over 100, because it's impossible to roll one dice and get it to be a 1 and a 6. We're still going to end up with 55 over 100, which is 11/20. Let's take a look at number 8. For number 8, it says find the probability of rolling a number greater than 2 and then rolling a multiple of 3 when a number cube is rolled twice. Well, really, the probability that you roll a number greater than 2 on a number dice is really, there's 4 rolls out of 6. All right, so there's, because you could have been rolling, what, a 3, a 4, a 5, or a 6 out of a 1, 2, 3, 4, 5, or 6. So that's 4 out of 6. And then we multiply that by the probability of getting a multiple of 3. Well, on a roll of a dice, 1, 2, 3, 4, 5, 6, how many of these are multiples of 3? Well, the 3 is a multiple of 3, and the 6 is a multiple of 3. So that's how we get 2 over 6. And when we multiply those together, then we end up getting 8 over 36, which does reduce to 2/9. So that's your probability. Was this necessary? Probably not, because we're just rolling a dice 2 times. So you could figure it out this way, but you do not have to figure it out that way. Let's take a look at number 9. A drawer contains 8 blue socks, 8 black socks, 4 white socks. Socks are picked at random. Explain why the events of picking a blue sock and then another blue sock are dependent, then find the probability. Well, I wrote the probability of picking a blue sock on the second pull is different based on what you pulled out of the drawer the first time, so they are dependent. All right, what's the probability that you pick a blue sock on the first go around? Well, there's 20 socks altogether, so the probability of drawing a blue is going to be 8 out of 20. But now we're not putting that first sock back, so the probability of drawing another blue is going to be 7 out of 19, because there's 7 blue left out of 19 total. And you go ahead and you multiply that out, and it is whatever it is as your answer. I'll let you fill that in. Okay. For number 10, it says 2 cards are drawn from a deck of 52. Determine whether the events are independent or dependent and find the indicated probability. Selecting 2 face cards when the first card is replaced would be independent. So a jack, a queen, a king, those are your face cards. All right. So there are 3 face cards for every suit, and there's 5 suits. So I could even write 3 face cards per suit times 4 suits. Suits divide out, and we're left with 12 face cards. So what's the probability of drawing a face card in your deck? Well, it's going to be 12 over 52. But what if we put that card back, right? We're replacing that card and we're doing the experiment again. Well, then we got to multiply by another 12 over 52. And when you work this out, you end up getting 9 over 169 when you reduce your fraction. What if we're going to select 2 face cards when the first card is not replaced? Well, if it's not replaced, then that means this is a dependent situation because your second draw of a card is dependent on what you drew the first time around. So the first time we draw, well, our probability of getting a face card is still 12 over 52. But the second time we draw, since we did not put the card back, we're down to 51 cards in the deck, and 11 of them are going to be face cards, right? Assuming that we pulled a face card the first time. So we get 12 over 52 times 11 over 51. That reduces to this fraction of 11 over 221. All right, how about number 11? At a juice bottling factory, quality control technicians randomly select bottles and mark them pass or fail. The manager randomly selects the results of 50 tests and organizes the data by shift and result. The table below shows these results. So this is the table that you were given here, and then you needed to fill in the joint and the marginal frequencies. So this all adds up to, what does it add up to? 24, 35, 40, 50, right? Adds up to 50. So when you take 14 divided by 50, you get 0.28. If you take 10 divided by 50, you get 0.2. 11 divided by 50 is 0.22, and so on. When you add up all those passes, that adds up to be 0.7. Now we know this number down here has to be 1 always when you do these joint and marginal frequencies. And you can do 5 over 50 and you get 0.1, 4 over 50 is 0.08, and so on. And we can add these up and we end up getting 0.38, 0.28, 0.34. That adds up to 1, and the 0.7 and the 0.3 add up to 1 also. So now that we have that table, what is the probability that a bottle was inspected in the afternoon given that it failed the inspection? Well, let me clean this up a little bit so we can talk about this. So, given that it failed the inspection, if it says given that it failed the inspection, we're going to focus just on the fail column of our relative frequencies chart. All right, and it says what's the probability that a bottle was inspected in the afternoon given that it failed the inspection? Well, here's the frequencies that we're interested in. 0.08 out of the total, which is 0.3. So if we do 0.08 divided by 0.3, we get 0.2667. What's the probability that a bottle failed the inspection given that it was inspected in the morning? Well, now we don't want to highlight the failed column anymore. We want to highlight what's given here, and the given is that it was inspected in the morning. All right, so if it was inspected in the morning, that would mean that we want to kind of highlight the morning information. And what's the probability that the bottle failed the inspection? Well, I see failed in the morning is 0.1 out of the total of 0.38. So if I take 0.1 divided by 0.38, I end up getting 0.26316. All right, that brings us to number 12, which says you have a deck of 52 cards. Explain why the events choosing a club and choosing a heart are mutually exclusive. Well, you cannot choose a card that is both a heart and a club, so that's why they're mutually exclusive. So what's the probability of choosing a club or a heart? Remember, if it's an or situation, you need to use plus. And don't forget that we could say it's the probability of choosing a club or a heart is the probability of choosing a club plus the probability of choosing heart minus the probability of choosing a club and a heart. But remember, we said that they're mutually exclusive. That means this probability of choosing a club or a heart is really just equal to 0. So we end up getting probability of choosing a club. Well, that's 1 out of 4 cards are clubs, right? Because there's 13 clubs out of 52. That reduces to 1/4. How about the probability of drawing a heart? Again, 13 hearts in the deck out of 52 cards, because that's one of the 4 suits. So that's 1/4, and we add 1/4 plus 1/4, and we get our answer of 1/2. Let's take a look at number 13. It says the numbers 1 through 9 are written on cards and placed in a bag. Find each probability. The probability of choosing a multiple of 3 or an even number. Well, the probability of choosing a multiple of 3 or an even number is going to be the probability of choosing a multiple of 3 plus the probability of choosing an even minus the probability of choosing an even multiple of 3. Well, out of these 9 numbers that are in the bag, 1 through 9, the probability that you pull a multiple of 3 would be 3 out of 9. Why? Because there's 3 multiples of 3 in the bag. There's 3, there's 6, there's 9, out of the total 9 numbers. So it's going to be 3 out of 9. What's the probability that you draw an even number out of the bag? Well, there's 2, there's 4, there's 6, there's 8. There's 4 even numbers in the bag out of the 9 numbers in the bag. So that's 4 out of 9. Minus, what's the probability of drawing an even multiple of 3? Well, out of these multiples of 3, there was only one even multiple of 3. So that's only getting a 1 out of 9. There's a 1 out of 9 chance of pulling an even multiple of 3. So overall, we get 7 over 9 minus 1 over 9 is 6 over 9, which is 2/3. All right, now what's the probability of choosing a multiple of 4 or an even number? Well, the probability of choosing a multiple of 4 or an even number is going to be the probability that you draw a multiple of 4 plus the probability that you draw an even minus the probability of drawing an even multiple of 4. Well, the probability of drawing a multiple of 4 is just picking a 4 or an 8. There's only 2 possibilities out of 9 possibilities. So that's 2/9. What's the probability of drawing an even? We talked about that. There's 4 ways to draw an even out of 9 ways to pick a card. So that's going to be 4/9. And what's the probability of drawing an even and a multiple of 4? Well, the multiples of 4 are both even, so it's the same 2 numbers out of 9 numbers. So that means that you're going to have minus 2 over 9. So 2 over 9 plus 4 over 9 minus 2 over 9 leaves us just with 4 over 9 as our answer. All right, let's take a look at number... Somehow it looks like I missed number 14. Oh dear. Okay, so we'll have to come back to that. Here's number 15. Each of 4 students randomly chooses a pen from 9 styles. What is the probability that at least 2 students choose the same style? Well, remember, we want to find the probability that at least 2 students choose the same. That's the complement of each choosing a different style. So let's do the complement formula, which is 1 minus the probability that they each choose a different one, and let's actually figure out the probability that they each choose a different one. Well, that's going to be 9 choose 4, which is 9 factorial over 9 minus 4 factorial. That's going to be 9 factorial over 5 factorial. That's 9 times 8 times 7 times 6. That's 3,240. That's just the number, right? So this is just equal to this, but we want to divide by the total different ways that these 4 students can randomly choose a pen from 9 different styles, and that is 9 times 9 times 9 times 9, or 9 to the 4th. So when we take 3,024 and divide by 9 to the 4th, we get 112 over 243. So that should be the probability that they each choose a different style. And then the probability that that at least 2 students chose the same style is going to be 1 minus that, 112 over 243. So we are getting 131 over 243 as our answer. All right, so let me see if I can find number 14. There it is. And the probability, let's see, of the 570 people, 365 were male and 368 had brown hair. Of those with brown hair, 108 were female. So what is the probability that a person was male or had brown hair? So let's fill in this chart with what we know. We know that there were 570 people total, so that is, so that's this number right here. And then out of that, we know that there were 365 that were male. So I can put the total male at 365. And we knew that 368 had brown hair, so I can make the total brown hair 368. And I also know that 108 of those with brown hair were female. So I can fill in 108 right here. And then I can subtract 368 minus 108 and get this number here of 260. All right, and since I know there's 260 brown hair males and 365 total, I can subtract to get the number of males without brown hair, and that would be this 105 here. All right, I know that if the total people are 570 and 365 of them were male, that leaves 205 females. And since 108 of those 205 had brown hair, that leaves 97 with not brown hair. And that likewise leaves 202 for the total without brown hair. So that means I can fill these numbers into my table. I can fill in 260 male brown haired people right there in this intersection of the male and the brown hair. There's 105 males that do not have brown hair, so that number goes out here. And there are 108 females with brown hair, so that number goes here. And who's not in the male and who's not in the brown hair? That would be females without brown hair, and there are 97 of them, so that's why we see a 97 outside both ovals in our Venn diagram. So what's the probability that a person was male or had brown hair? That's going to be the probability that they're male plus the probability that they have brown hair minus the probability that it's a male with brown hair. We can get all of these from our chart or our Venn diagram. The probability that you are a male would be 365 out of 570. So that's 365 over 570. What's the probability that you have brown hair? Well, that's 368 out of our 570. And that means we've got plus 368 over 570. What's the probability that you are a male with brown hair? Well, the males with brown hair would be 260 out of our total of 570. And so that means we would have minus 260 over 570. When we work out the math here, we get 473 over 570. All right, so that answers that question. I think we've done them all now, and I hope that you are feeling more confident and ready to take the test. And we'll see you next time.